In this lecture, we want to talk about how to utilize phasors to solve circuits that are AC circuits. So just kind of going over the different techniques that we've used in the past and how there's a little bit of change and variation and looking at some examples. So the first thing is, remember, phasors are indicated with bold in the textbooks. When I write notes, I indicate them with a little squiggle on the top. The first thing to say is that Kirchhoff's voltage law holds and is exactly the same in the frequency/phasor domain as it is in time domain, as is KCL. So our previous KVL and KCL equations that we learned and the related mesh current and node voltage method will apply to the phasor domain. Also, impedances. So once a capacitor and or inductor has been converted to an impedance, and then impedances behave like resistors. So impedances in series will add, impedances in parallel will add as inverses. So one thing to define is that just like in resistance, we defined 1 over the resistance as the conductance. In impedance, we define 1 over the impedance as the admittance, and it's indicated with a Y. Admittances combine like conductances do. So they would have the opposite, because they're equal to 1 over Z, they would have the opposite behavior as an impedance. Sometimes it's easy to talk about admittance when you're talking about capacitance because then it becomes j omega c for the admittance rather than 1 over j omega c for the impedance. There is going to be an example in this series of lectures that works with admittance. As a general rule, in this class and in Circuits 2, that's not something that I really work with much. So we'll show the example, but you can just as easily do that with impedances. So also voltage division works perfectly fine in the frequency domain, where in this case, if you wanted the voltage across an impedance that's indicated with subscript J, you would just take Z sub J over the sum of all the impedances multiplied by the voltage that's across all of them in series, and that would give you the voltage across the independent ones. So voltage division works. And I should also say that current division works as well, although it's not indicated in the slides. So just looking at some examples, the first one that we want to look at is, and I'm just going to kind of step through these examples. They are typed up. There is one that I will add some MATLAB and sort of some problem-solving techniques to what's in the information, what's in the textbook that I took these examples from. But we'll step through some examples. So here's one. This is a circuit. It's sketched in the time domain. You're given the current from a current source here, and you're asked to do several things stepwise. Calculate the frequency domain equivalent circuit. This is the problem that has the equivalent admittance. So we're basically looking at these two terminals and trying to determine what is the equivalent admittance when we look into the two terminals. So once again, admittance is 1 over impedance. Impedance is add like resistors. Admittance is analogous to conductance. So admittance is 1 over Z. So admittances in parallel will add. Okay, so we'll look at that when we get to that part. Then we'll use that to find the phasor voltage V and find the phasor current using current division. So first of all, and then we'll go back to the time domain to find steady state expressions for V and I. So when you talk about currents and voltages in the time domain, there's different terminology depending on what textbook, what class. So sometimes these are referred to, when you go back to the time domain, sometimes these are referred to as instantaneous currents and voltages. Instantaneous is just a word for function of time. Other times they're referred to as steady state currents and voltages. And then sometimes people will just say find the voltage in the time domain or find V of t. All right, so the first thing we do is we do a phasor transform of each individual element. So let's go back. We're going to take this current and change it to a phasor. That would be 8 angle 0. That's what will appear here. and this lowercase I sub s will go to an uppercase phasor indication. The resistor will remain the same. This resistor will remain the same. This inductor will go to j omega L, where omega is 200,000. And this capacitor will go to minus j over omega c, where once again omega is 200,000. So here is the result of the frequency domain equivalent circuit. Now once we have converted to the phasor domain, the inductor becomes an impedance, the capacitor becomes an impedance, and so we can then treat them as impedances or admittances. So to find the admittance in each branch, we take 1 over the impedance. So go back and look at the circuit real quick. So we're going to take 1 over 10, and then we're going to take 1 over j8 plus 6, and then we'll take 1 over minus j plus 5, and look at these as admittances. So that's what's done here. The units are Siemens. So we've taken 1 over each z to obtain y1, y2, and y3. And the advantage of that is that then you can find y equivalent by adding all three together. So just as a complex number review, we add together the real parts, so the 0.1 and the 0.06 would give us 0.16, the minus j 0.08 and the j 0.2. When we add those together, we get plus j 0.12. So real numbers and imaginary numbers exist like in parallel universes. So that's how you do that addition. Then it was converted to the phasor domain, and when I did the screenshot, the lower bar of the little angle sign, so this is not 0.2 divided by, should be an angle indicator. It just got cut off in the screenshot. So if we convert that to the phasor domain, to polar form, we get 0.2 angle 36.87 degrees. That's maybe a few too many significant digits, but it's okay. So why would we convert back to polar form? Because typically when you're working with currents and voltages, you're using Ohm's law, so you've got multiplication or division times an impedance or admittance, depending on what you're working with. That's easier to do when you have it in polar form. And so that's done right here. To find z equivalent, we take 1 over y equivalent. Now let's talk about division. So we would have 1 over this. So the way you do that is you first work with the magnitude. So you would find the actual numerical value of 1 over 0.2. The angle, remember, is represented by e to the j theta. And if that's in the denominator, as it is when you take 1 over y, then that's just going to come up as an e to the minus j theta by rules of exponentials. So in the phasor form, all you really have to do to move the angle from the denominator to the numerator is to give it a negative sign. So you can see here the negative 36.87. You can see here the 5. Okay, now let's go back and look at the circuit again and see what else we're asked to find. So we were asked to find this voltage V, which in the phasor domain circuit was this voltage. Now remember what we did is everything to the right we converted to a single impedance. So we have a Z. So to find V here, we would just take the current in the phasor domain and multiply it by the impedance in the phasor domain. And once again, you cannot mix phasors and cosine functions. You can't mix time and frequency. You're either or, so if you're working in the phasor domain, everything is in the phasor domain. So here then is our voltage. We took our Z equivalent, which was right here. We multiplied that by the current, the phasor current, which was 8 angle 0, in order to get this voltage here. Okay, we now can find the current by basically taking the current through all of the admittances and employing the current divider rule. And when we do that, we get 4 angle minus 90 for the phasor current. I would actually do it this way because that seems like a really weird and awkward kind of way to do a current divider. So we knew the phasor voltage from this step, 40 angle minus 36.87. If you come back to your circuit, everything in this circuit is in parallel. So if I want this current, I can just take my voltage and I can divide by that total impedance. In my opinion, just a much more straightforward way of finding the current. Either way, this is the result, which is basically what you want. Okay, so now the last part of the question asks us to go back to the time domain. So V of t and I of t. So let's come back. So our V of t, our V, the phasor, had a magnitude of 40 and a phase angle of minus 36.87. So I take the magnitude and the phase and I literally plug them back in as the magnitude and the phase, and the cosine function has the same omega t. So everything, every current and voltage in this problem has t in common. It will all be cosine of 200,000 t, and then we'll have a magnitude and a phase that vary depending on what current and voltage we're actually looking at. So for the current and voltage, you just take the magnitude and phase from the phasor domain, and you substitute it into this form, and go back to the time domain. Okay, that was that. You can also do source transformation in the frequency domain. It's done exactly like you would do it in the time domain, except you're working with an impedance instead of a resistance. You can also form a Thevenin equivalent, except in this case you have an equivalent impedance, and it would be a equivalent voltage, that would be a phasor. And in fact, we next unit. So here's what that frequency domain Thevenin equivalent circuit looks like, and here's the frequency domain Norton equivalent circuit. It is perfectly possible and reasonable to contain both independent and dependent sources, in which case doing that kind of Thevenin equivalent calculation can become extremely tedious because you're doing basically the same thing we did in the material we worked with on Thevenin equivalent, but you're doing it with complex numbers, so it can become extremely tedious. All right, here's an example where you're asked to do a series of source transformations to find the phasor voltage in the circuit below. So we're just going to apply repeated source transformations to where we get a single loop circuit so that it's easy to solve for current and then voltage, or we can use voltage divider, either way. So we'll do a series of source transformations, which means I'm going to take this voltage source in series with this impedance and transform it to a current source in parallel first. So that should be done right here. Yeah, so here's your current source, 4 minus J12, in parallel with that impedance. Now, how do you get that? Well, you take your original voltage and you find a current, which means you take 40 angle 0 and you divide by 1 plus J3. Now, how do you actually do that? The best thing to do is, if you don't know how to do that, go back to the videos that talk about complex number manipulation. You can also find a lot of example videos on YouTube and Khan Academy. So the easiest thing to do is to take your 1 plus J3 and convert that to polar form. Once again, if you don't know how to convert to polar form, that's something you absolutely need to learn how to do before the last exam. So you would convert 1 plus J3 to polar form. You would take 40 angle 0, divide by 1 plus J3, and what you should get is 4 minus J12. And then the 1 plus J3 appears in parallel. You then look at the parallel combination of these two. So that would be the product over the sum to get an equivalent impedance here. That gives you 1.8 plus J 2.4. Once again, you work with the J like it's almost like it's algebraically. So you would do this, as the product of two binomials. So you would have 9 plus J 27 minus J 3 minus J squared 9, which would give you plus 9. So once again, if you need to review on how to manipulate that, you can. I'll show you later on how to do that in MATLAB, because it's something you can also do in MATLAB, and many of you will have calculators which can multiply, divide, and add complex numbers. But you do need to understand how to convert from one to the other and how to do the complex number math. All right, so I find that parallel impedance, equivalent impedance, and that replaces these two branches with a single impedance, a single branch. I can then do another source transformation, which means I take my current source and I multiply that by my new equivalent impedance, and that gives me a voltage source. And that impedance that was here, that 1.8 plus J24, is going to appear in series with that voltage source, which should be on the next slide. So here's our 1.8 plus J24 that was taken up in the source transformation. Here's our voltage source, and now we can find the current by taking the voltage and dividing by the total impedance. So every impedance is added up, real parts are added, imaginary parts are added. We do the division and come up with this for the current, phasor current. We then can find the voltage by taking the phasor current and multiplying by the impedance. So I'm going to end you could also use voltage divider. I'm going to end the video here because it's getting a little bit long, and we'll take up with the additional examples in the next video.